Hi, all. Good morning. Welcome. This is the CAE Fall 2023 seminar series. I'm very glad to welcome Professor Lisa Burris from The Ohio State University. She is an assistant professor in civil, environmental, and geodetic engineering there. She earned her BS in architectural engineering, an MS in civil engineering. These were from Kansas State University, and her PhD was in civil engineering from the University of Texas at Austin. She is passionate about improving the quality and sustainability of concrete infrastructure through her research and teaching work, and her research experience lies in the general area of multi-scale physical and chemical issues in cement-based materials. She's won numerous awards, published a lot of papers, and gotten a lot of funding. I'm not going to go into the details of those so that she can take center stage. Thank you very much, Professor Burris, for taking the time, and it's all yours.
Great. Thanks, Prannoy. I'm really excited to talk to you guys today about a kind of specialty area of research that we're working on at Ohio State. But let's start first with Prannoy did a little bit of introduction, but I'm originally a native of Leavenworth, Kansas. That's located smack in the middle of the country. I think it's actually very close to the actual geographical center, and it's home to something very famous called the Big House, which is the largest federal penitentiary in the United States. So that's the most exciting thing about my hometown of 50,000 people. From there, I did 2 degrees at Kansas State University, starting out in architectural engineering, where I became really interested in buildings and structures, and pursued a master's in structural engineering, and then converted over into the concrete materials world, and completing a PhD and then a postdoc, which was at Georgia Institute of Technology. I've been here at Ohio State since 2017. And I have a picture here of my family. Everyone's a year older now, but I have 3 boys, 8 and under, so they're 8, 6, and 3. And so my side hobby other than concrete is dinosaurs and Batman right now. My research group here, I've named it the Cement Research Group, the Cementitious Materials Novel Technologies Research Group. And our overall mission is to really understand the chemical reactions and interactions with environment of our cementitious systems with the goal of increasing sustainability and durability. And we're doing that through novel uses of cements and concrete. So I look a lot at alternative cements, alternative SCMs, which Prannoy and I have been working on together a little bit. We've created and tested bacterial concrete. We've tested plastics in concrete, and now we're looking at hempcrete as well. And along the idea of novel materials, we've started down a path of novel uses of concrete as well. So I have a patent for floating ultra lightweight concrete, which is shown down here, which we're using to float plants out into Ohio watersheds that have an overgrowth of algae due to misuse of fertilizer for farm fields. Ohio is a big farming area of the country, and it causes the algae to overgrow, and they emit a cytotoxin, which is a brain poison. And so during the summer, some of our communities in Ohio can't actually drink the water from their local lakes. We're also working now with hempcrete. As I mentioned, we're using it for insulation and also just to 3D print it. And then the other novel thing that we've done that I'm proud of is our Pervious Concrete work I'm going to talk to you about today. So what are we talking about when we think about acid mine drainage? This is a picture of a lake out in eastern Ohio that's called Dead Lake. And it's called that because everything around it is dead. And you can see the incredible color of the lake. And that is due to high levels of dissolved heavy metals, specifically aluminum, present in the water. And so these lakes look really pretty. And they actually told me that they had a Spartan race trudge through here, swim through here as part of the race, which is kind of horrifying. This is also at pH 4, so probably all of their skin was really stinging when they got out of the water. But this is a big problem in the areas of Ohio where we've had mining of coal over the past century or so. This is another picture of that lake. A couple months later, the reclamation services that work with this area of the state drained the lake a little bit to try and reduce the pH and move some of the contaminated water out and hopefully have it filtered by the soil itself. And then here am I and my collaborator on this project, Ryan Winston, who's an environmental engineer and studies water chemistry, out collecting samples from that lake. And so a couple things you notice, again, the kind of gross looking green color, but also around the lake, everything is dead and it's orange. That is indicative of the main cause of formation of acid mine drainage, which is iron that has been unearthed and no longer covered by topsoil. And so that interacts with rain and causes the acid mine drainage. More on that later. So this site is located at a really special place in Ohio called the Wilds. After the American Electric Power Company was finished mining coal from this area, they deeded all of the land back to the state, or they donated it back to the state. And half of it is now this savanna area where they have mainly African kind of safari animals, and you can go on a bus tour and like ride next to the rhinos and see them. It's also home to the country's and maybe the world's largest rhinoceros breeding program. So it's pretty fun, but they're concerned about the quality of water because of the presence of the animals on the site and overall just for general reclamation. So when I think about coal mining, this is kind of the picture that I have always had in my head. And this is what happens in our neighboring state of West Virginia, where you have people that tunnel down into a mountain to dig out the coal, and they truck it out with carts, and everybody's covered in soot and black. But this kind of mining doesn't generally cause acid mine drainage. Instead, in Ohio, what we have happening is strip mining. And so when we do strip mining, we're essentially just stripping away layers of the soil and to get down to the coal. And then when we get to the coal, stripping that away as well and moving that off site. And so what you see with strip mining is these giant scoops taking layers of the soil out, and then they'll separate out the industrially important components, in this case, the coal or not. And so this will occur over very wide areas of land, huge expanses of land, and then it's obviously exposed to the elements again. And so at our particular site at the Wilds was the home of the Big Muskie. And so a little history for you. This is the largest piece of man-made equipment ever built on the world. And you can see here the little scoop that's scooping the coal out. And on the side of this picture here, we show a marching band standing in the remnants of that scoop. And you can actually go and see the scoop and get in it yourself and take pictures. I have some pictures which I won't bore you with, but it's a huge machine, a huge scoop removing just massive quantities of material. So you can see here it moved more than 483 million cubic yards of material over its lifetime. So this is a very intense removal of soil and disturbance to the local environment. Oh, I will bore you with it. There's me in the Big Muskie scoop. All right, so this area that we're looking at is about a 10,000 acre site located in kind of the eastern area of Ohio. And there, you'd be probably surprised to know that power companies actually have played a big role in the reclamation of land. Their goal was not just to disturb things and walk away and leave it a horrendous site. They have tried to revert the land back to a usable state. And depending on our knowledge of what works for reclamation, those approaches have changed over time. So in the top half of the map here, the northern section, that is where mining occurred during what was called the tree law era. And so the belief then was that as long as you replant trees after you're done mining, everything will grow back and be as normal and great. And so that's what the mining companies did. Was after they were finished with the site, let's go back to this picture, there were all of these hills and valleys. They left all of those alone and they spread tree seeds out to regrow the forest in that area. But what has happened is it's created low points and lots of places for rain to spill over and move throughout the environment and create new streams and ponds, and that has contributed to this acid mine drainage issue. The southern half of the area is actually not as plagued by acid mine drainage. So this blue area here, they mined during the secondary period of reclamation, which is the grass law area. And so they recognized the problems the tree planting was having. And so now the mining companies are required to remove the topsoil layer and set it aside. When they finish mining, they have to smooth out the area and make it more rolling hills. They'll bring the topsoil back in and they replant with grass. But in order to keep the dirt from blowing away, they also have to compact that soil down, and that actually prevents natural trees and shrubs from moving into the area. So we end up with those large kind of grass savanna areas. So there's no perfect way to reclaim, but that has stemmed the occurrence of acid mine drainage. And so I'm overlaying here a map of pH in the area. And so you can see in the tree law era, we have some pretty low pH regions down to about pH 3, which kills plants, wildlife, and strips it actually dissolves heavy metals from the soil as well. So this is the area in which our materials from the study were located. And you can see another one of the sites here. This is a large stream that has become a set of lakes. They traveled down in elevation, and there were for a little while beavers that had moved in and built some beaver dams at the edge of the pond, causing it to kind of pool up. The beavers also were helpful because their dams that they built helped to actually filter the water and provided a natural sort of reclamation of the acid mine drainage problem. But they have since moved on and not returned. Probably they had a hard time finding anything to eat because the water is quite acidic. So I've been alluding to acid mine drainage this time for a while, but let's talk about what acid mine drainage actually is. So when we have strip mined the area, we've taken soil from down below the topsoil and upended it and exposed it to air and water. Our soil, or our rocks and minerals on the Earth's surface, are naturally very full of iron. We separate out that iron ore to make steel and other products, but when it's in the soil, it will react with oxygen in the air and water from rain or other water that the site may be exposed to. And when that happens, it will deprotonate and release hydrogens, which go into the water. So those hydrogen elements, or the charged ions, enter the water and acidify it and cause the pH to drop. And so you can see what happens as we acidify the water. Between pH 6 and 9, it's pretty harmless and in kind of a natural state. Below 6, we begin to change the ecology of the area. Things start to die off: fish, plankton, algae first, and then larger organisms, fish and salamanders after that. It prevents the maturance of their young, so all of the embryos and eggs die, and then those areas become essentially deserts, or food deserts for other animals. So after the death of the fish and salamander, you'll also start to see things like deer move out of the area because there's just not plants and other organisms that animals that hunt, not deer, but foxes and things like that. They don't have any food sources in that area. In addition to the reduction in pH being bad for animal life, we also start to dissolve heavy metals out of rocks and soil when we have acidic water conditions. So you can see the types of metals that would go into the water: arsenic, cadmium, lead, manganese, and mercury. And all of these are linked with problems for human growth. We have brain dysfunction, developmental delays, blood pressure and kidney damage, nervous system damage, all sorts of things. And these also occur in wildlife, although we don't track IQ of wildlife, right? So it's harder to track, but the same sorts of things affect both the humans in the area and the plant life. And actually, down from the stream I showed you on the previous slide, there are multiple farms and farmhouses. So there are people living in the area who most likely have wells, and hopefully they've had those checked and are filtering their water because they're probably very heavy in heavy metals. So this is a big problem. It's a problem for animals. It's a problem for plants. It's a problem for people in the area. It also impedes the ability of people in these areas to use their watersheds for recreational activity. And so it reduces any ability for them to make money off of visitors to the area who would come to vacation for the weekend as well. So there's both ecological and economic impacts from acid mine drainage. So we wanted to look at a way to perhaps fix that. Oh, and then in addition, so this is not just an Ohio problem. Acid mine drainage is growing in severity around the world. The most significant and worst watersheds I've seen are in South Africa, and where they're doing a lot of mining of minerals and gold and diamonds. But you can see all across the world, we have abandoned mine sites for different minerals, and many of these have issues with mine water. Another major problem of this is that because it's originating from the soil itself, and we have a huge amount of surface area of the earth that's exposed to air and water pretty easily, acid can be generated in these sites for hundreds and hundreds of years. You don't have one reaction and then it stops and you no longer have a problem, but it continues to regenerate over millennia. And we can control it with some chemical means, but it's really not cheap. This chart shows the cost to reclaim several AMD affected creeks in Ohio. And you can see that it amounted to more than $30 million over, I believe, about a 10-year period. $40 billion per year is spent globally for AMD treatment as well. So 30 million in Ohio, multiplied by orders of magnitude across the globe. So if we could solve this with a cheap, widely available, simple to construct material like concrete, that would be a huge benefit. One of the ways that we currently treat acid mine drainage is with lime dosing, and that's what I'm showing here. So you would install at the side of your creek a giant silo that holds lime, and over time it's going to mix with water and put out that slurry into the stream. But you might notice the stream looks awful. I would definitely not want to swim in that. And it probably is, I mean, you don't see any resolution and beautiful plant life, flora and fauna spawning near that creek as well. So we have to install ugly things out in our beautiful nature preserve. We have to monitor it and restock the chemicals, maintain the functioning of the equipment. And then we create kind of a nastier situation when we use a lime treatment system. But that also might spur an idea of, if we're using lime to treat this already, perhaps we could use lime in another way or another high calcium material to help treat the acid mine drainage. And that was our idea. With pervious concrete, we know that CSH forms very, very high surface area microstructure. It's often made using a lime-based material, limestone, and some of our sources of fly ash are also very high in calcium. It has a very high natural pH. So even if we don't see any absorption of minerals from that high surface area, perhaps we can just mitigate some of the pH with our naturally alkaline material. The other benefits of using pervious concrete is that it's available really everywhere. It's very inexpensive to make. It's easy to make. Someone without a degree can make it, and typical construction companies, no problem. And the other thought that we had when starting this is that perhaps we could install something that would completely non-interrupt the stream. So we would allow streams to flow at a continued rate. We wouldn't be creating a dam sort of situation and creating new lakes and taking over people's land, but instead we could self-treat located within the stream. And so this is kind of the idea that I had, was to create a panel system where we would incorporate it into the stream. We'll have the water flow through it. We'll solve for the AMD. So our study had 3 objectives. We wanted to understand the mixture design parameters associated with making pervious concrete and understand how wide of a range of flow conditions we could run through that pervious concrete without impeding water flow. We wanted to understand the ability to remove heavy metals and increase pH from that system. And we wanted to track and understand the durability of the pervious concrete. How long can we expect these things to live and exist before we have to replace them? So we'll start first with study objective number 1 of concrete mix design. So we're making a pervious concrete. You can see the 3 types of mixes we used below. We used one with a number 8, so pretty small pea gravel, a large limestone, number 56, that's a 1.5 inch max aggregate size aggregate, and then a number 8 limestone. We tested over 30 mixes with varying water to cement ratio, varying proportions of cement to aggregate, and varying amounts of sand incorporated into the aggregate to really tweak the flow of the water. And so what we learned from this is that there's a pretty, I was going to say direct, but you can see that they have a little bit different relationship. But there's a strong relationship between density and porosity. So as we decrease our density, we're going to be increasing the porosity of the mix. And that's going to translate to increased permeability as well. And so we were able to model the relationship between porosity and density and permeability to enable later prediction of properties that we want for our particular stream. So if I know the stream flow rate, I can enter that into my permeability graph and determine the amount of porosity I have. And then I can do a quick check of my mix design by checking the density during production of the concrete. And so we were able to design mixes that had flow rates of between 0.5 and 4.5 centimeters per second, which seemed pretty fast in the lab. You turn on the water spigot and the water flows right through the pervious concrete. But unfortunately, a typical river flow is about 134 centimeters per second. So what we know from this is we're not going to be able to insert these panels into a large river and treat the entire thing. It's going to be just too much water flow and too much restriction from the pervious concrete. The streams, like the picture I showed before, though, are a little bit different situation. Sometimes you have streams that aren't flowing 100% of the time. They may dry up and restart with rainfall, and many of them are flowing quite slowly. So this could work for a stream, we believe, and we're about to test that actually out at the wilds later this month. And so although we may not always be able to match the stream flow, the other thing that we can do with this data is use it to control the amount of contact time between the water and the pervious concrete. So if we enable the water, if we give each water ion a longer interaction period with the cement surface, then we may enable greater removal of ions during that higher reaction time. And that may allow us to reduce the amount of wall that we need to install to do treatment. Some other things that we learned from the phase where we looked at concrete mix design, we looked at water to cement ratio, and we found that we actually had a drop in porosity as we increased our water to cement ratio. I have a little figure kind of trying to explain that here. This is directly related to the paste volume and the size of the pores that is created from your aggregates. And so we have the number 8 limestone in blue here, and the pea gravel, approximately the same size aggregates, and we see that direct relationship between reduced porosity and increased water cement ratio here. And so we can see what happens is that as we increase our water cement ratio, we are increasing the total paste volume, and so we're decreasing the amount of pore space that results in between these aggregates. And granted, this is a little bit simplified and things would pack a little bit differently in real life, but it gives a good picture in your head of what's happening. So as we increase water cement ratio, we increase paste fraction, our paste volume, and we decrease our total porosity. And then with our large size aggregate, we actually saw very little change in porosity, and that's simply because there's a lot more porosity that's created in that large aggregate size mix. We can go back to the picture here, and you can see the size of the voids in between these aggregates is just significantly higher, and so it kind of overemphasizes the amount of porosity, and the change in volume of the paste has a lot less effect at that point. So if you're working with small aggregates, you need to take into account what water cement ratio you're using. If you're using a larger aggregate mix, then it's less impactful overall. We also found that we could control porosity by varying the cement to aggregate ratio. So if we fill the spaces with more cement, as we saw in the previous picture, we're going to reduce our porosity. And so we can directly control porosity by that variance as well. And so we were able to develop with this direct relationships between density, porosity, permeability, and compressive strength. And that enables us to try to predict the properties that we want in our mix based on, we can predict the properties that we'll achieve based on another one that we target, or we can design our mixes to have a specific porosity or a specific compressive strength. We chose a mix which is located at the center of these red lines. That was between, it was about 25% porosity, as we were targeting about 1,000 PSI in strength. The Pervious concrete, because of the amount of holes and void space in it, the porosity, has a much lower strength than our typical concrete. And so we were shooting for just achieving enough compressive strength to support the loads of the water flowing through and maintain cohesion of the material, but enabling a high porosity level. And so you can see the closeness of our predicted values and what we were seeking and what we achieved when we measured our created concrete. In some cases, they're pretty close. Density and porosity seemed to agree with our model fairly well. The compressive strength and permeability both had quite a bit of variance from our intended value. All right, before we move on, any questions about mix design? Or should I not take questions for Noi?
However you please, but we usually do it at the end.
Okay, well, we can do that then. All right, so second portion, and I think honestly the more exciting part of the study was looking at the ability of the pervious concrete to remove heavy metals and adjust pH. And going into this, we had done a little bit of preliminary investigation where we just ponded a cube in a vat of acidic water. And we saw that it took about 3 days for the concrete to change the pH from a very acidic pH of about 2 up to a pH of 11. So we saw a very rapid increase in pH and mitigation of those acidic conditions. And we saw it over and over. So the drop in pH is where we changed out the solution and then waited again to see if we could re-increase the pH or if the cement and the alkaline component of the cement had been consumed. And so you can see we did it 3 times in a row. And so from here, we began to pursue funding and look to investigate this a little bit more. And so one thing that we needed to know in order to run the study was what is in the acid mine drainage and what compounds should we focus on understanding removal of. And so you can see acid mine drainage locations throughout the world. They tend to be high in iron because that causes that acidic production of the acidic water, high in aluminum, and manganese and copper tend to be, and zinc as well, tend to be the highest contaminants within acid mine drainage. A previous study that had been looking at remediation of groundwater had noted ability of the concrete to remove zinc. So we decided instead to focus on the iron, aluminum, manganese, and copper for our study. And you can see that our actual AMD values are down here. For some reason, we had very little iron in the sample, but we did have quite high levels of aluminum, manganese, and no copper. But you can see the human health criteria for the manganese specifically, we are orders of magnitude above it. So something that we could really look at improving. So for water testing, we suspended 2-inch pervious cubes, so rather small samples, in a liter of synthetic solution. We tested both with single ion metal solutions, so just iron sulfate, just aluminum by itself. We also made synthetic AMD solutions that had proportions more similar to the natural AMD material. And then we also tested the natural AMD that we retrieved from the site. We kept the water rotating or filtering through the pervious concrete using a stir bar. And so we used a very high proportion of metals in solution with the goal of trying to understand what the limits of absorption or precipitation of the metals from solution were. So 1 millimole is going to be much, much higher than you would ever find in nature. But we wanted to just see if we could reach the end of life of the cube. We exposed the cube to this water for 24 hours, tracking changes in metal concentrations over time. And then we repeated this with the same samples 3 times and trying to reach that breakthrough point. We tracked metal removal in standard OPC pervious concrete, and we also tested it with a number of cement substitutes, different types of fly ash, ground limestone, natural zeolite, and flue gas desulfurization product, which is often found at mine sites. And so we were thinking, let's use up something that could be located on site for in these areas. So our first exciting find was the visual evidence of removal of metals from the water. So you can see two cubes here. The one on the left was ponded in the alumina solution. The one on the right was ponded in the iron solution. And the water in both of these cases looks now very clear. It didn't start out that way. And you can also compare it to the removal of the metal just from change in pH. We had a theory that precipitation could be occurring just due to increases in pH in the water. And so we also tested a sample where we just added a sodium hydroxide to that acidic water to increase the pH. And we saw precipitation of, in this case, the iron from water with increase in pH. But the water is still quite cloudy, and you can see all of the particles floating through. And the exciting thing about our pervious concrete sample is that everything adhered to the surface of the concrete. So this is it's really awesome, I think, because you could place this out in nature, and instead of precipitating iron onto the soil to be redissolved later when the acidity of the water changes, it would precipitate onto your filter, and you could remove it from the site and remove that problem forever. So that was exciting. We saw also very rapid and almost total removal of ions from water. So on the top here, we're showing removal initial change in initial concentration. When we reach 100, that would be a removal of everything in the water relative to time. So it took about an hour for the majority of removal to begin. And by about a 2-hour time, we had removed the vast majority of all the metals present in the water. So you can see we're reaching levels up to nearly 100% in the aluminum, the iron, and the copper solution. And you can see that this is pretty closely linked to pH. So as we increase pH, we see a big jump in removal across very small pH ranges. And so we know then that the removal and the precipitation of materials is due to that change in pH. Compare that to the manganese, for which we were only able to remove about 40% of the material. But manganese precipitates out at a pH of around 9 to 10. And so this is going to be due instead probably to adsorption and kind of a magnetic catching of the ions on the surface of our CSH material. And you can see the difference in pH range over which adsorption occurs is pretty distinct between those that are precipitating out due to the change in pH and the manganese, which has kind of a continuous decrease in ion concentration over time. So what we learned overall from this is that we can really effectively remove metals that have acidic precipitation levels. And we still are somewhat successful in removing the manganese that doesn't respond to kind of a neutral pH range, but at a lower rate. I'm sorry, I forgot where I put my boxes here. All right. And we've just talked about this. So the specific precipitation on the concrete surface itself does appear to be contributing in the case of the manganese. But it is not playing in much in the case of the other materials. So this chart on the top is now not removal by concrete. This is the removal by changing the pH in our control solutions. So with the addition of sodium hydroxide. So we see similar removal levels of aluminum and blue here occurring as occurred in the concrete samples. And so it is the pH itself that's causing precipitation of the material, or of the metals from the water. We still have that benefit of that it's happening on the surface of the concrete. So we probably have a micro surface extreme pH increase right at the surface of the concrete that's causing everything to adhere to it. And then compare that again to the manganese. We saw an increase in the range where the manganese precipitated out at higher pH, but we still see a removal of that material before that level as well. And here's a picture of what all of the samples looked like after ponding. So the bottom sample was just our control that was in lime water. And then we have aluminum and this is the manganese, iron, and copper. And so you can really clearly see what ion was removed based on the color of the concrete, and I can almost kind of tell how effective it is in doing that as well. So I'm looking forward to seeing this out in the field, where we might be able to visualize when it's time to remove that filter. So we also tested with our Class F and Class C fly ash and limestone mixtures to see if use of any of those materials improved or changed the ability to remove metals from solution. And overall, they appear to function pretty similarly. So this is a positive in that we know however we make our pervious concrete, it will have the same ability to remove ions from water. We did see a slight improvement in all cases with use of the limestone, which is shown in yellow. So the yellow box here shows the location where we expect precipitation to occur based on pH. And you can see in all cases that the limestone is removing metals from water at a little bit earlier, lower pH level. So we don't require as much increase in pH from the alkalinity of the concrete in order to remove equal amounts of the metals from the water. And that happened for aluminum. That also happened slightly for iron. And it was very apparent for the copper, and manganese didn't seem to be as affected. So it suggests to me that using a calcium material can help to remove higher amounts of metals from your system. So we also wanted to test this in not such a lab kind of setup. And so we constructed a column. You can see it out here. This got a little bit more professional as we went along. This is one of our first tries. But we have created a PVC column. We're putting cylinders now of our pervious concrete inside of a gasketed rubber sleeve that will make sure that the water goes through the pervious concrete and not around the pervious concrete. And we refiltered the solution up to 70 times and tracked the removal of ions based on numbers of pass-throughs of the water through the system. Okay. And we saw very similar performance with our column testing. If you look at the chart down below, this shows a comparison of aluminum removed by the cube that was ponded in solution and the aluminum removed from the column setup, and then also the manganese setups as well. And so you can see that our very lab-based testing with the cube ponded in solution very closely mirrored what happens as the water filters through that pervious filter. And over time, we were able to remove up to 99% of the aluminum, and that correlated. We calculated the number of pass-throughs and translated that over into a sorry, I'm having trouble seeing my charts behind the Zoom. So the number of pass-throughs, each one was 6 inches, multiplied that by the number of recirculations that we had of the pore solution, and that gives us a length of the wall that we would expect. And so if we have a 5.6 meter wall, we should be able to remove 100% of the aluminum from solution. And you can see that, again, that correlates with an increase in pH over time. The manganese was much less effective. We were able to remove much less of that from this flow through kind of setup, which was a little bit disheartening. But it does look like things that are controlled by acidity, we will still be able to filter in the field. And we can test other compounds in the lab and get pretty similar results. And so taking that a little bit further, comparing the results from the cubes and the columns, we were able to generate an estimation of transference of lab solution exposure time to the filter length you would need in the field. So we can now predict if I create a 4 meter length filter, that should correspond to the amount of metals removed from solution at about 100 minutes. And so we can guesstimate the length of the wall needed to fix our particular situation based on the results from these two setups. Right, so the last set of objectives that we looked at were trying to understand the durability of this system, both in terms of how much water can be treated and how long it will remove ions from solution, as well as tracking degradation of strength over time. Concrete is naturally not very resistant to acid and can be broken down pretty quickly through exposure to acidic solutions. Okay, so first, let's talk about how long the system will work. And by work, I mean change the pH, remove precipitate out the heavy metals. And so this dark blue line here shows our change in the time that it took to reach pH 7 after we ponded a set of cubes in a pH 2 sulfuric acid solution. And so ponded the cubes in solution, had my student come in each day to check changes in pH, and when it reached 7, we recorded that time. And so what we see over time is about a 12-hour difference from week 1 to, or well, week 10 to up to week 50 in the time it took to increase to pH 7. That would be a pretty significant increase in wall length if you're wanting your water to stay trapped in that wall for 12 extra hours. So you could extend and over-design the wall to ensure that your water is inside of the treatment filter for longer. Or this may suggest that over time we're going to lose the effectiveness of the filter and we'll need to replace it within the year. Right. And then in addition, so we were able to neutralize 52 times the volume of each of the cubes throughout this year of testing, with honestly not a lot of degradation in pH increasability if we give it a little bit more time. So with that amount of water per 2-inch cube, that suggests that we can treat an immense amount of water. And remember that this was at pH 2, and our stream flow out of the wilds was pH 4. So that increases the amount of water we can treat by 2 orders of magnitude. And so it will translate to 288 cubic yards of water treatable for each 2-inch pervious concrete cube, which, if you know Americans, we don't like to use the metric system. So that could be 224 million washing machines, or 3 of our Ohio Stadium football stadiums full of water. So theoretically, with the amount of water treatment we were able to achieve in the lab, we could treat an almost endless volume of water in the field. Granted, there are pretty significant changes in system components. We're not just putting water into one system and allowing it to change all the way up to pH 7, we're instead allowing it to flow through a filter. So we're going to achieve a little bit less in the field, but this suggests that the system from a treatment perspective has almost endless capacity and can be used for many years to remove heavy metals and mitigate pH concerns. As far as compressive strength goes, we actually saw much less degradation and loss of strength over time than I was expecting. Overall, over about a year, we saw about 400 PSI drop in strength. So our initial cubes for this set started at a compressive strength of around 1600 PSI. And by the end, we're at about 1200 PSI. So that suggests that and I'm not sure what the actual failure level of the system will be because it doesn't have honestly that much in terms of loads filtering into the pervious concrete. But if we assume a PSI of 400 means that the wall will start falling apart, that suggests that from a durability standpoint, we can use this system for 3 years. So I see that I've talked too fast and we're not anywhere close to the end time here, but our future for this is to scale up. We think we've shown some pretty effective heavy metals and pH mitigation ability from our in-lab samples and our flow-through samples. And so we're looking now to scale up and test this at a real site. So we have gotten some funding from the university and are going to be installing a site a filter at the site that I showed before out in the wilds within the next month. We're going to test a lot of things that were really difficult to track in the lab. We're going to look at clogging potential, how fast the water just gets gummed up with dirt and sediment in front of the filter. And that is part of the reason for this kind of odd filter design as well. So we've designed a set of panels that are about 4 inches thick. That way, when the first one clogs up, we can pull it out, remove it, and then we'll have a whole new filter that's not clogged after it. We're also going to be checking actual lifespan. How long do we see any measurable change in pH and removal of heavy metals? How long does the concrete hold up out in nature? We're going to be checking pH before the water enters the panel setup and after. We're going to be looking a little bit at filter design and how we can best design a filter with minimum amount of concrete to meet the needs of our system, and also account for heavy rains and overflows of water due to those kinds of situations. We're also going to be looking at changes in to organisms in the area. So are they happy that we're mitigating the water a little bit, or do they dislike having concrete kind of shoved into the middle of their stream? And then we're also going to do a little bit further work with the concrete and using some scanning electron microscopy to section samples out and see where the metals embed within that cementitious microstructure. And so I'm showing here a picture of the site where we're installing the panel. So here is our large AMD pond and the location of the old beaver dam. And then the stream flows out and narrows in size. So we've created some trapezoidal panels that are 4 inches or 4 feet on the top, 3 on the bottom, and are about a foot tall. You can see that the stream is pretty shallow. And so we don't believe that even when we have heavy rains that there'll be too much overflow from the panels. We've cast and are planning to install 16 4-inch panels, which doesn't get us anywhere near that 5-meter length, but we're hoping just to be able to see some change as the water goes through the filter, and then we can re-examine our kind of modeling of filter length at a later time. Also looking at expanding our applications for this technology. So we want to look at groundwater. John Kevern from the University of Missouri, Kansas City has done a bunch of work looking at groundwater and pervious concrete, but I'm really excited to look into that as well. And we're going to examine the removal of heavy metals dissolved from solar panels that have been placed in landfills. There was an EPA article about this last summer where they're having tremendous contamination of the water in California due to the people reaching end of life on their solar panels. And then we're also talking with our local water officials about ideas of how to incorporate this into municipal systems. We didn't actually achieve drinkable water quality with any of the pervious concrete exposed water. And so we would still need to have some municipal water treatment, but it would remove the vast majority of contaminants and water. And so our hope is that we could decrease the cost for water treatment through use of pervious concrete. And so I do want to acknowledge everyone who's helped with this project. We were funded by this Women in Philanthropy group at The Ohio State University. They're kind of separate from the university, but just a group of women that pool money and try to fund things that they view as beneficial and impactful. The department has supported several of the undergrads on the project, who include Finn Hahn and Ravi Patel that I've listed there. Our major grad student was Sam Riekert, and then we've had a lot of research assistants from other people in the department, Yujamin, Dr. Jay Liu, and Wild's personnel as well, Rebecca Swab and Janelle Urich. So I would love to answer questions. I see there's a couple chats, which I assume